Hello everyone. Today we are going to talk about power series. What are power series? Let me remind you how geometric series looks. Like a standard geometric series. Standard geometric series is going to look like this, right? A r to the power of n minus 1 and n starting with 1 to infinity, and generally it's going to look like this. ar square, and so on, right? Here A is the first term and R is a ratio. And everything is a constant here. A is a constant and R is a constant, right? Now, imagine that you are going to change this constant, allow R to be a variable. This way you can describe several geometric series, right? For example, when R is equal to 1/2, that's one geometric series. When r equals to 1/3 is another geometric series, and can be, for example, r can be 1/square root of 2. It's going to be a third geometric series. So r can be a variable, and our geometric series are going to become a power series. So let me write down power series as a definition. So definition. Power series are going to look very much like geometric series. The little difference is going to be that we are going to start power series with 0. Well, actually, when n equals 0 over here, that's still going to give you power of 0, right? If you imagine like n equals 1 in geometric series, power of r is equal to 0 for the first term. Here it's going to be same. And it's going to look like C0, C1x, C2x squared, C3x cubed, and so on. What are going to be C's over here? For geometric series, the coefficient is always same. That's A. Here, we allow the coefficient take different values. So C0, C1, and so on are just constants. And in our case, they're just real numbers or like any natural numbers. X, it's a real number, it's a variable. And X belongs to the real numbers. My R didn't look very good. So X is any real number. Kind of very strange, interesting series. Let's consider a simple example of such series. Imagine that all C's are equal to 1. So C1 equals 1 equals C2 equals, sorry, C0 equals 1 equals C1 equals C2, and all of them are equal to 1. And my power series are going to look like this. 1 plus x squared plus x cubed and plus all lots of other terms. They're going to look like a long infinite polynomial, right? Just normally we start polynomial with the highest power, but because here the highest power is infinity, we're going to start our polynomial with like the lowest power. What we know about the sum of such a series? Well, because this series looks exactly like G series, and A of G series, the first term is equal to 1, this is A, and the ratio of this series, one which you kind of multiply every time, is just x. So you multiply the previous term by x, so my ratio is equal to x. I'm going to apply the standard formula for G series. The sum of the series is going to be A over 1 minus 1. If you still remember this formula we learned in section 2 of this chapter, it's 1 over 1 minus x. Well, what does it mean? It means that the sum, infinite sum of terms we have is going to be equal a very simple function, 1 over 1 minus x. This is just a function of x, right? And here we have infinite series. By the way, maybe I should write down this series in sigma notation. Sigma notation is going to look like this: x to the power of n from 0 to infinity. When actually this sum exists, remember that sum exists for geometric series only when r is less than 1, right? Convergent. In our case, we are going to have x less than 1. So this series convergent when absolute value of x is less than 1. So for all x is less than 1, it's going to be a convergent series, and the sum of series is going to be 1 over 1 minus x. Interesting, right? So why do we need to represent such simple function as 1 over 1 minus x as a sum of series? Well, generally speaking, yes, function is much better than sum of infinite series, right? But in some cases, function is going to be too complicated. And the sum of power series is just a polynomial. And we know that everything with polynomial is very easy. Like it's very easy to differentiate all these power functions. It's very easy to integrate these power functions. And sometimes it's going to be helpful to us. Okay. Now, guys, one more definition. Actually, we can have this power series a little bit. Let me write it down. I'm going to label this power series centered at 0. So the first definition was about power series centered at 0. Now, guys, if we change a little bit the shape of my power series, keep the constant same way, but we are going to subtract some value from x, some constant value, x0, for example. You can start with 0 to infinity and have it like c0, c1, x minus x0, c2, x minus x0 squared, and so on. This is going to be power series centered at x0. Sorry, x0. So why actually they are centered power series and why this at 0 and this is at like x0? Well, you probably see that in parentheses here we subtract x0, but if we say x0 equals to 0, we are going to get this power series, right? If we set up x0 equals to 0, we are going to have nothing subtracted from x. Now the question is, why are we calling it centered? I'm going to explain it on example. Why actually it's going to be, what kind of center of series it's going to be if series is just a sum, it's not a circle, right? Let's see. So my example number 2. Let's consider a series looking like this. Sigma n equals 0 to infinity. X minus 3 to the power of n divided over n. Nice power series, right? So what is what over here? According to my definition, my x0 here equals what? 3, right? My coefficients are going to be equal 1 over n. You don't need to write it down every time. I'm trying to show like what is what in this series. When this series is convergent, usually we are interested, right? Because our series are going to look a lot like geometric series. We are going to use a ratio or root test on them to test for convergence. So let's try it. So ratio test. Limit of an plus 1 over n goes to infinity. So what is my an plus 1? And guys, here we do need to do absolute value. Why? Because this x minus 3 can take positive values and negative values. For example, if x equals 4, that's a positive value, right? 4 minus 3 is 1. But when x equals, for example, 2, that's going to be 2 minus 3 negative. That's going to be negative value. So I'm going to keep absolute value until the very, very end here. let me write down like all my terms, all my factors increased by 1 unit. Put absolute value and kind of simplify it a little bit, combining again similar factors together. So x minus 3 to the power of n plus 1 divided over x minus 3 to the power of n multiplied by n over n plus 1. Here, guys, what I'm going to do, I'm going to simplify a little bit expression with my x's. So I see that that's x minus 3n plus 1 and n. So I'm going to cancel n and I'm going to just keep x minus 3. Here I'm going to divide both numerator and denominator by n. So I'm going to get 1 over 1 plus 1 over n. Absolute value, n goes to infinity. We know that when n goes to infinity, this term will go to 0 and the whole thing will go to 1, right? My final answer is going to be x minus 3 absolute value. You see that I still keep absolute value. Why? Again, because x is a variable and I don't know like what is going to be x minus 3, positive or negative. So that's my answer. Now, well, according to my ratio test, to make it convergent, I'll need to make it less than 1 because that's the value of my limit, right? Well, what I have over here is inequality. There are two ways to solve this inequality. And you guys can use the first way or the second way. I'm going to do the first way first because we kind of learn it in like calculus maybe or somewhat in algebra. So when absolute value is less than something means that the function inside of absolute value is less than 1 and greater than negative 1. Usually that's two inequalities together when you have it like this. I'm going to write down a less than b is equivalent that a is less than b and greater than negative b. This is the rule. So, oh, my 1 doesn't look like 1. I'm sorry. Even worse. Now, what I can do with this inequality? Well, I'm going to add 3 on both sides, plus 3, or not both sides, actually, all 3 sides. And I'm going to have 2x and 4. So, guys, I have an equality for my x. I'm going to draw my x on number line, and I'm going to draw 2 over here and 4 over here. And where is going to be the center of this interval? So in this interval, the series is convergent. What's the center of this interval? The center of this interval between 2 and 4 is 3. That's exactly our x0. And that's why we call this series centered at 3, because actually center of interval of convergence is going to be 3. Now, what is going to happen over here? Over here and over here. We remember that from the test, when x minus 3 is greater than 1, series is divergent. So I'm going to put divergent here, and convergent here, right? The only 2 points we'll need to investigate, which are left on number line, are these points, this and this. Because remember that test is inconclusive, and we'll need to apply some kind of different tests on the series. And that's what I'm going to do. So what are different tests on the series? Well, I'm just going to plug in x equals 2 into my series. How my series is going to look, what I'm going to do, original series, and I'm going to plug x equals 2. And you guys are going to do the same when you investigate the endpoints. So x equals 2 is going to give me 2 minus 3 to the power of n over n, which is 2 minus 3 is what? Minus 1 to the power of n over n. And well, I should not probably use n from 0 to infinity. Actually, I did a mistake in the beginning somewhere because remember that we are dividing by n over here. Yeah, let me fix it from 1 to infinity. Otherwise, everything is good. So now I just need to fix this 0. Should pay more attention to that. And guys, you probably recognize what? Harmonic series, alternating. This is alternating. harmonic. What do we know about alternating harmonic? So I'm going to blacken this point because it's convergent. Now, guys, what is going to happen at x equals 4? We have 4 minus 3 to the power of n over n goes from 1 to infinity. And that's going to give us 1 over n from 1 to infinity. And this is also harmonic, just normal harmonic. And normal harmonic is divergent. So this point is going to be out. Let me put convergent next to the series, otherwise it doesn't look like. Okay, so this one is alternating harmonic convergent. This one is just harmonic divergent. And if I write down my solution now, I'm going to write down that x is between 2 and 4. So at 2, it's convergent. At 4, it's already divergent. That's going to be my interval of convergence. Interval of convergence. Talking about method number 2 of solving this inequality. Well, guys, when you have x minus 3 less than 1, it's like you draw a circle of radius 1 from point 3. I'm going to do that, well, maybe next to it, just to show you that you are going to get exactly similar picture, or maybe over here. Let me draw a circle. Imagine that you put a compass over here and just use radius equals to 1 and draw a circle with this radius. Oh, that's going to be a circle. And point 3 is going to be exactly center of this circle. You see? So guys, though interval is not really a circle, it's kind of one-dimensional circle, we are going to call this one radius of convergence. I'm going to write it down separately somewhere here. So inequality x minus a less than r, if you get inequality x minus a less than r, when you do the test, r is going to be radius of convergence. A, center, right? And ends of the interval are usually supposed to be checked separately. Okay? So you can also write down the interval like this. X belongs in the interval 2 included, 4 excluded. Interval notation, right? You can write down as inequality or interval notation. Basically, guys, for all power series, we are going to be very interested in interval of convergence, and we are going to kind of use first the ratio and root tests, and then maybe investigate the ends of the interval. Okay. What other situations we can have when we have power series? So that was example number 2, right? Example number 2. Let's do example number 3. Example number 3. Example number 3. Let's consider a series which looks like n factorial x to the power of n from 0 to infinity. Here we don't divide by anything suspicious, so I'm going to consider this. And let's use a ratio test right away. Ratio test, limit an plus 1 over an, absolute value, n goes to infinity. So let's have it. Limit. So we have n plus 1 factorial by x to the power of n plus 1 over n factorial by x to the power of n. N goes to infinity. Let's simplify it. So we remember that n plus 1 factorial, it's actually n plus 1 multiplied by n factorial, and we're going to cancel n factorial. Here, x to the power of n and x to the power of n can be canceled, and we have n plus 1 multiplied by x absolute value, n goes to infinity. Well, guys, generally, what is going to happen here? X usually is going to be set up to a certain number. For example, you set up x equals 1, for example, and bring n to infinity. What is going to be the result? 1 multiplied by infinity, infinity. 2 multiplied by infinity, infinity. 0.1 multiplied by infinity, still infinity. So this limit is going to be equal infinity for every x, except the one x, which is going to turn it into 0, right? When x is equal to 0, the limit is going to be 0, just because this expression will be 0 and limit of 0 is 0. So actually, guys, this series is convergent only for x equals 0. For all others, because 0 is less than 1, and this one is definitely greater than 1, right? For all other x's, it's going to be divergent. Well, what is going to be the interval in this case? Well, if it's convergent only at one point, we're going to say that the radius is equal to 0. And we are going to give no interval. We are going to just say that there are only one point of convergence, x equals 0. By the way, x equals 0 here is the center of the series. So convergent only in the center. Well, if your series is centered at some other point, for example, x minus 3 here, it's going to be convergent only at 3, because only when x equals 3, it's going to be equal to 0, and limit is going to be equal to 0. Otherwise, limit will be always equal to infinity. See? So can happen. In the previous example, the radius was equal to 1, and we had some interval of convergence. In this example, radius equals to 0, and there is no actually interval, right? We just have one point. In my last example is going to be power series x to the power of n divided over n factorial, n from 0 to infinity. Here, guys, I can place n equals 0, because probably, guys, you remember that 0 factorial equals to 1. Okay, let's check the ratio test. Guys, I'm going to just put x n plus 1 here, n plus 1 factorial, and here x to the power of n factorial, and kind of close my absolute value. Again, I keep here absolute value because I don't know what is my x going to do, and can be positive or negative. So let's simplify this expression. X to the power of n plus 1 over x to the power of n, and here n factorial over n plus 1 factorial, right? And goes to infinity. And let's kind of start working with x. Well, here is n plus 1 axis, here is just n axis, we are going to cancel, right? For n plus 1 factorial, it's n plus 1 by n factorial, right? Because we multiply all the numbers, and n factorial can be canceled, and my limit is going to become absolute value of x, 1x is going to stay here, right? And n plus 1 over here. Now, guys, this is going to be a special limit too. Why? Because x usually is going to be a given number, like you choose x equals 1 or 2 when you kind of use your series, right? So no matter which number you have instead of x, when you bring denominator to infinity, it's going to give you a limit which is going to be equal to what? To 0. And 0 is always less than 1. So this series is going to be convergent for all x belonging to rational number or real numbers. We're going to say in this case that x x belongs to interval of convergence. That's going to be the whole number line. right? It's going to be the radius in this case. Well, the radius is going to be infinity, just because like if you find the center of this interval, it goes into infinity in both cases, right? Okay, so guys, what we've seen three different examples. On example number one, we had, let me go back and show you like all three examples at one place. Kind of hard to do, but if you do it very, very small. On example number one, we had some interval of convergence, right? On example number two, I mean example number three, let's say, we had only 1 point for convergence. Did I write down the radius here? Well, I did not write down the radius, but the radius was equal to 1 here, right? The radius is equal to 0 at only 1 point. The radius is equal to a number, and you have the interval. In the last example, the radius equals to infinity, and interval is actually all number line. This is going to be the case for all power series. So I'm going to summarize it into a theorem, which is kind of, which is describing like all possible outcomes of the power series. Okay, make it bigger again so I can write down the squares. Move it all of this way. So okay, theorem. So theorem is going to sound like this. For the power series general power series x minus a to the power of n. Yeah, guys, I used x0. You can label this point, the center, any way you like. In the book, they label it as a, and I generally like label it as x0. First, can be convergent on interval. And R is going to be called radius. And divergent on outside of the interval. We don't know about endpoints because my power series test, my ratio test, is not kind of telling us anything. But at least inside of the interval is going to be convergent, outside divergent. Endpoints, we'll need to investigate more. Number two, convergent at x equals a. Only when this term is, no, this factor x minus a is equal to 0, which happens when x equals a. And then the radius is going to be equal to 0. Or convergent for all x. And the radius is going to be equal to infinity. Okay, now guys, I want to go back to the last example where we had this radius equal to infinity. What kind of series it was? Oh guys, this is a special phenomenon series. We don't know it yet, but if you work with this series and find the sum of this series, like I did for the very first series in this section, you're going to figure out that the sum of this series is going to roll into a function e to the power of x. Very interesting, right? Well, that's a special exponential series. And we are going to talk about this later. But for now, you can start looking at this series and memorizing it. By the end of this class, if you like, I will be very, very happy. Like if after half a year, you will still remember that e to the power of x can be represented as a series x to the power of n over n factorial, which is not difficult to remember, I guess. Right? Okay. So So basically, guys, what do we need to know about power series is that sometimes they are like 1 point where they converge, sometimes they have like the whole number line where they converge, and sometimes they have the interval of convergence. I think I'm going to consider one more example of finding of the interval of convergence, okay? And I think that's going to be all for this section. Okay, guys, I'm going to consider pretty complicated example. I don't remember, it was 1, 2, 3, 4, maybe example number 5. So I'm going to find the radius of convergence and the interval of convergence for this nice series. And I don't know why, but the book has it from n equals 1 to infinity. Okay, so as you probably remember, we are going to start with a ratio test. So ratio test is going to give us a limit and approaches infinity. And here you will need to write down term n plus 1, 3x plus 1, n plus 1 over 4, n plus 1. And here 3x plus 1 to the power of n, 4 to the power of n. I'm going to simplify a little bit my expression by combining similar terms together. So 3x plus 1 to the power of n plus 1 over 3x plus 1 to the power of n, and 4 to the power of n over 4 to the power of n plus 1. Here I was so lucky. I can cancel 3x plus 1 nth power and 3x plus 1 nth power. It's 1, which is going to be left, which is 3x plus 1 to the power of 1, right? And here 4 to the power of n and 4 to the power of. So my result is going to look like 3x plus 1 left over from my first fraction and 4 in denominator left over from my second fraction. N goes to infinity. Well, guys, because I have no n here, that's going to be just my final answer. So my final answer is going to be 3x plus 1 less than 4. It's my limit. According to my ratio test, my limit must be equal than 1. Must be less than 1 to make it convergent. Well, how do we deal with this inequality? Guys, what I'm going to do, please watch. And here I'm going to show you the second method of dealing with inequality. So remember, my goal is to get inequality looking like this. X minus a less than r, right? That's going to be my goal. So I'm going to bring this inequality to that one. I'm going to write down 3x plus 1 over 4 less than 1 and start working. I'm going to multiply by 4 both. Well, 4 is sitting under absolute value, but 4 is a positive number. So I'm going to cancel it here and get 4 here. 3x plus 1 absolute value less than 4. My next step, comparing to this expression, I have just x and here I have 3x. I'm going to divide by 3 both sides. So I'm going to get what? X over here plus 1 over 3 less than 4 over 3. Okay, my inequality now looks like this one, right? So what is my r? Well, my r, according to inequality, is 4 over 3. What is my center, a? My center a is negative 1 over 3. Looks a little bit crazy because we always have minus a, but here we have plus, means that it's actually x minus negative 3. Now, guys, I'm going to draw a picture of the interval. So I don't really need to solve this inequality. I'm going to do, guys, I'm going to draw number line. Label negative 1 over 3 as my center, right? And then imagine that I draw a circle with radius 4 over 3 around. Circle. So 1 over minus 1 over 3 plus 4 over 3 is going to give me what? Just 1, right? Minus 1 over 3 minus 4 over 3 on this side is going to give me minus 5 over 3, which is not that nice as 1, but if possible. Yeah. So what is going to be my interval? These numbers in between. If you solve this inequality standard way, hopefully I didn't do any mistake anyway, you are going to get the very, very similar answer. Let me double check it. Yeah, looks fine. Now, guys, as you probably remember, the inside of this circle of convergence is going to be convergence. Outside, divergent. This is divergent. Divergent. Black one is convergent. And now we need to investigate endpoints. My endpoints are minus 5 over 3. And my next endpoint is 1. I'm going to start with negative 1. Remember, we plug in the point right into the series, what we have. So the series is going to look like minus 5 over 3. So 3 and minus 5 over 3 plus 1 to the power of n divided over 4 to the power of n, and goes from 1 to infinity. It's going to be equal. I should probably put x equals 1 lower. Well, 3 is going to cancel, right? Minus 5 plus 1 is going to give me minus 4 to the power of n. And here 4 to the power of n, and from 1 to infinity. Well, basically, guys, if I simplify it, I'm going to get minus 1 to the power of n, and from 1 to infinity. You know what is this? This is going to be minus 1 plus 1 minus 1 plus 1. We already know that the series like this is divergent because the sequence of partial sums is not going to be converging. It's going to be alternating between 0 and 1, 0 and 1, 0 and 1, 0 and 1. Okay, so at this endpoint is divergent. Let's check another endpoint. X equals what? 1 over 3, no, not 1 over 3, just 1. Right? So what we have? N equals 1 to infinity, and we have 3 by 1 plus 1 to the power of n, 4 to the power of 1. What do we have here? Well, 3 by 1 is 3 plus 1, 4, 4 to the power of n over 4 to the power of n from 1 to infinity is going to give me a sum of ones. We know that sum of ones is equal to infinity. Infinitely many ones is going to give us infinity. Also divergent. Okay, so when we write down our final answer, we're going to say that my interval of convergence is from negative 5 over 3 to 1, and both points are not included. Radius is going to be equal 4 over 3. And that's going to be the final answer to this problem. Endpoints are not included because endpoints, it's going to be divergent. And that's how it's going to look on the quiz. Like, investigate the series and find the interval of convergence and radius of convergence. Okay, that's all for our series. And we are going to have more power series, but they're going to be like more specific power series. Okay.